Today we're going to see an explanation about two-dimensional finite elements and their basic equations and how we obtain nodal values in two-dimensional elements. So here we go. Here you have a two-dimensional, let's just make it perhaps a simple triangular element, okay? And I'm going to put in here a picture in here that we can take a look at in here. This is XY plane, so my finite element is I, J, and K. We will do the counterclockwise convention in here to explain what we are going to do and in that sequence, right? Because we could go the other way, but we have to adopt the labeling convention counterclockwise starting at the node I, which is arbitrarily defined. The question is here, and the objective is find the shape functions when you have a two-dimensional finite element, and also find the distribution of the solution of phi over the element. This is the question. So let's try to explain a little better here what we see in the picture. So the green triangle here is the finite element in here, a two-dimensional finite element, triangular element in here. And the blue triangle that you see above, is the solution phi. The solution phi obviously is a projection of the element. It's also a triangle and it's also a plane. Okay, just like we in one-dimensional elements use linear interpolation, and we said that the solution within a one-dimensional element was aligned, was linear, yeah. We are going to use the convention here that the solution is a plane. In fact, it's like we use linear interpolation and it comes from there. So that concept in 2D is a plane. So in here we have a situation where you have the I, J, and K counterclockwise. For the solution also we would have phi sub I, phi sub j, and phi sub k. Okay? And the equation of this plane would be alpha 1 plus alpha 2 plus alpha 3 coefficients, and this time we have x and y. Before we only had this, because what is highlighted there is the equation of a line, right? But we know now that the equation of a plane would be when we include the y factor here. So this is the equation of a plane. So we have set the ground rules. We have the elementary finite element in 2D and the elementary solution of the finite element in 2D. Okay, what are we going to do now? The objective, remember what it is? Find the shape functions and also find the distribution over the finite element. That's what we need. So, and here we're going to do, all right, we're going to say the solution phi at the node I will have to be whatever these coefficients are with the coordinates of the node I. So in here, we have what we call the interpolating polynomial, which is in fact a plane here. So phi sub I at x sub I and y sub I. And phi sub j, so at x s sub j and y sub j, and phi sub k at x equals x sub k and y sub k. So these are coordinate pairs. Yeah, these are coordinate pairs. Okay, so now we have that we could perfectly write an equation of the solution for the node phi as a function of the coordinates. Remember, the coordinates I, j, and k are given. We know them. Why do we know them? We know them because we are dealing with a physical device, with a physical region that we are trying to model, trying to analyze. So you see in here we have phi sub I, phi sub j, and phi sub k, and we have used the interpolating equation to put the coordinate pairs, and in here obviously we know all the x I, x sub j, and x sub k, and y sub I, y sub j, and y sub k. We don't know the coefficients, okay? But you see, just like we did in one-dimensional element, you have in here a set of three equations, three linear equations in here. So that is this one right here. Okay, those are the three equations that we are dealing with. Okay, so far so good. Okay. If we have a set of linear equations here, and the unknowns are the coefficients alpha 1, alpha 2, and alpha 3, it follows that using Cramer's rule, we should be able to solve this. Okay? So if we do it here for alpha 2, for example, how do we do this? We put in the numerator, we're gonna get a determinant composed of the constant values, which are phi sub I, phi sub j, and phi sub k, and this will be x sub I, x sub j, and x sub k, and then then y sub I, y sub j, and y sub k over here. And in here, if we expand on Cramer's rule, then we are going to obtain what you see here. You will have phi sub I times the minor, which is like this, and that's what you see here. Then you'll have phi sub j times the minor, like that, which you see over here. Then you have phi sub k times the minor, and then you have it here. Okay? So these are for the first one, I sub I, sub j, and I sub k. For the second one, if you obtain this for the second value of alpha 2, then you have the matrices a little different, yeah? and then you will have b times phi sub I, b sub j, phi sub j, and b times phi sub k. And finally, alpha 3, we would replace it in using, on this column, put the constants. That's how you see it over here. Then you have a 1 and an x of I and an x of j. And you do this. So for alpha 1, alpha 2, and alpha 3 is what we have in here. So if we know these coefficients, alpha 1, alpha 2, and alpha 3, since we know the form of the solution, which is a plane, we know the corresponding shape functions because the solution now is going to become like it is in here. See this factor right here, times phi, this factor times phi sub j, and this factor times phi sub k. We learned in one dimension, if you put the solution in terms of the nodal values and the shape functions, it's not, it is obvious to conclude that these factors would be the shape functions. So if we summarize this operation over here for this is alpha 1, by the way, alpha 1, alpha 2, and alpha 3, then we can understand that these coefficients that we need are n sub I and n sub j and n sub k, and we are giving the values for a, I, b, I, and c sub I from the first equation, and then you have this from the second and this for the third equation. So once it ends up happening is that the shape functions are 1 over 2a, which is a is the area of the triangle. And if you expand this determinant here, you will see that that is exactly 2a. Okay, so the shape functions in 3D are given by these expressions. So in 3 dimensions, what am I saying in 3 dimensions? In 2 dimensions, I, j, and k, the shape functions are given by knowing the values of a, I, a, b, bi, and c sub I, as well as a sub j, b sub j, and c sub j, and a sub k, b sub k, and c sub k. And all these are dependent on the geometry. We start there. We know what the dimensions of the finite elements are. So, and that fulfills one of the objectives. And then the second objective is to find the distribution of phi over the element. Okay, so in here we will have to think about a little bit of the properties of the shape functions and what do these expressions actually mean. So n sub I, for example, is 1 over 2a times ai times bi times ci. I already show you what those were here, okay? So this is 2a on the denominator. If the values of the shape functions are x sub I and the nx the shape function as it is in here, x is equal to x sub j and y is equal to y sub j. If you do this, you're going to see that the shape function expression, this one right here, has a value of 1 at the node, and it has a value of 0 at the other two, like you see here. N sub j and n sub k is 0 at the other two. Okay, so these are some conclusions we can reach. The shape functions have value 1 at their own nodes and 0 at the other two. The shape functions varies linearly along the sides, and n sub j varies linearly along the side ij and ik. The shape function is 0 along the opposite side of the node, and n sub I is 0 along the side ij. Well, I think we need a little drawing here that we should be able to do it in 2D to explain this concept. Because it's one thing to just look at the mathematical value, but we should really see it with a sketch. So let's make one.